the review packet. This is just a review of all the material that we've done in this unit. So let's start. The first question is, a radioactive element decays by 2% each day. What is its half-life? So we know that we can model this with some kind of exponential function. So I'll just write a, b to the t. I don't know the initial amount, a, but I don't need it to solve the problem. What I do know is b, because I'm told that the amount of stuff decays by 2% every day. What that means is every day you lose 2%. If you want to lose or decrease by 2%, the question is, what do you multiply by? If you want to decrease something by 2%, then you should multiply by 0.98, because a loss of 2% means that after that loss, you will have 98% of what you started with. So every day, we are multiplying by 0.98, which means that my b value is 0.98. So this is the correct model. Every day I'm decreasing the amount of stuff by 0.98. Every day I'm losing 2%. Now the question is, what is the half-life? So if you remember what that means, it means how long does it take before the amount of stuff has decreased by a half? In other words, how long does it take for half of the material to disappear? Well, of course, y represents the current amount of stuff. If you want there to be half of what you started with, if you're interested in the time t for which y is half of what you initially had, then what you should do is replace y with 1/2 a. The reason behind that is the following. Basically, if a is the initial amount, then you want y to be 1/2 a, because that means that you currently have 1/2 of what you started with. In other words, one half-life has elapsed in time. So if you look at this equation, the a's can just be divided off, and we have 1/2 is equal to 0.98 to the t. This is an exponential equation. T is the only unknown. You can solve it by taking logarithms, and we find that natural log of 1/2 is equal to natural log of 0.98 to the t. And of course, as usual, this t here will come out on the side. So I have natural log of 1/2 is equal to t times natural log of 0.98. And of course, I can finally solve for t by dividing both sides by this natural log expression here. So I have natural log of 1/2 over natural log of 0.98. That's our t value. Now, if I'm trying to find my calculator, I thought I brought. Oh, here it is. So if you want a decimal approximation of what that actually is, we need to ask our calculator. So what is natural log of 1/2, which is 0.5, divided by natural log of 0.98? Looks like I get about 34.3. I guess that's days, right? 34.3 days. Okay, great. So moving on. Number 2, a radioactive element has a half-life of 30 years. By what percentage does the element decay each year? Let's start again by writing down just a general exponential model. I know that this thing has a half-life of 30 years, so I can say, hey, every so often I am multiplying by 30, which means I can say that b is 1/2. Or sorry, I think I said multiplying by 30. Of course, I meant multiplying by a half. Every so often I'm multiplying by a half. So if I replace b with a half, this model right here is almost right. As we've seen many times before, the issue is that you don't want to multiply it by a half every single year, but rather every 30 years, and that means we have to divide this exponent by 30. Okay, so that's the exponential model, and now the question is, by what percentage does the element decay each year? Well, to see what's happening every individual year, not every 30 years, we have to rewrite this expression so that the exponent t is by itself. So, of course, just as always, we have to rewrite this using the so-called power of a power rule. right? This expression can be rewritten as 1/2 to the power of 1/30th to the power of t, right? And now, if I just simplify using my calculator, that expression in brackets, it's 1/2 to the power of 1/30. Looks like I get 0.977 something. Okay. So this is our model rewritten so that the t is by itself. And as you can see, this is telling you what's happening every single year. Every year, you're multiplying by that number right there. Now, the question is, by what percentage does the element decay? In other words, by what percentage does the element decrease? If you're multiplying by 0.977, that means you're not losing 97%. You're losing like a little less than 3%. If you look at 1 minus 0.977, that will give you the percentage lost. So that's 0.0228. So in other words, we're losing about 2.28% every year. Okay. All right, so number 3 says a certain radioactive element has a half-life of 100 years. In a sample taken today, only 30% of the original element remains. How old is the sample? Okay, let's start with an exponential model. I know that I can model this thing using an exponential function. We're given information about half-life, so I should use 1/2 for b. Oh, and in this case, do I know the initial amount? I don't. I sort of, we'll get to that, but b I can represent as 1/2, and then as usual, since the half-life is 100 years, I write t over 100. That way I'm only multiplying by 1/2 every 100 years. Now, the question is, how old is the sample? Well, obviously, that means I'm being asked to find t. If you look right now, t is certainly not the only unknown. We need to replace y with something, right? We haven't used this information yet. It says, in a sample taken today, only 30% of the original element remains. Well, look, the amount of original element is represented by a, okay? So if the current amount is 30% of the original element, that means that the current amount, y, is 0.3a. Do you follow that argument? A is the original amount, and if we now have 30% of the original amount, then that means the current amount is 0.3 times the original amount, in other words, 0.3a. So we can replace y with 0.3a, leaving the right-hand side of the equation alone. What you notice now is that the a's can be divided off by both sides. So I have 0.3 is equal to 1/2 raised to the power of t over 100. And this is now an exponential equation that can be solved using logarithms. If I take the natural log of both sides, so that's 1/2 to the t over 100. Okay. As usual, this exponent of t over 100 will come down and be put on the side. So we have natural log of 0.3 is equal to t over 100, natural log of 1/2. And now you can get the t by itself. So I guess we would have t is equal to natural log of 0.3 times 100 over natural log of 1/2, which obviously we need our calculator to evaluate. So what is that? Natural log of 0.3 times 100 divided by natural log of 0.5 gives you 173.69. So that's how old the sample is. Okay, moving on, number 4. It says an investment of $200 is made in an account with 5.7% annual interest. Find the effective annual yield. If the interest is compounded annually, that's once per year, and then quarterly, monthly, continuously. Okay. First thing I want to say is that strangely, this piece of information is actually unnecessary. You don't need the 200 to find effective annual yield. To find effective annual yield, you just need to know the annual percentage increase and the number of times per year that interest is compounded. So if you like, we can use our, compound interest formula Here it is. Oops, that should be an n to the nt. So yeah, p is the initial amount, which is 200, and then 1 plus r is the percentage annual interest, written as a decimal. That's 0.057 over n, number of times compounded per year. In this example, in part A, we're compounding annually once per year, so n is 1. Raised to the nt, that's 1 times, well, we don't know what t is, it doesn't really matter. Okay, so simplifying, I have 200 times, if I simplify this expression in parentheses, of course I get just 1.057 raised to the 1 times t is just t, and since the t is by itself, that is telling me what is happening every individual year, which is what effective annual yield is all about. Every year I'm multiplying by this number, which means that every year I'm increasing by 5.7%. So in this case, the effective annual yield is 5.7%. Now, that makes sense because when you compound interest only once per year, the effective annual yield will be the same as the advertised annual interest rate. It's only when you begin compounding more often that these two numbers will be different. So let's look at B. It's exactly the same question. Everything's the same. You know, we can use the same formula. The only difference is that n, the number of times per year, will be different. N is now going to be 4 because we're compounding quarterly, raised to the 4t. So now here's the thing. In order to see what's happening every individual year, you have to rewrite this expression so that the t is by itself. We've done this many times. So that's going to be, all right, well, first of all, what's the expression inside the parentheses? It's 1 plus 0.057 over 4. So that's 1.01425 to the 4t. Now, of course, we can rewrite that as a power of a power, like 1.01425 to the 4th to the t. So that's the same thing. So what is this number to the 4th? It's 1.058, blah, blah, blah. So 1.05822 raised to the t. And now, written in this form, we can see that what we're doing every year is we're multiplying by this number here. Now, if you're multiplying by 1.058, that means that you're increasing by 5.822%, right? Which is a little bit more than 5.7%. Okay. Same thing. Now let's just do it monthly. Everything's the same. I'm not going to recopy everything. I'm just going to write 200 times 1 plus 0.057 is the same. All that's changing is the n. N is now monthly means 12 times per year. Okay. So raised to the nt, so that's 12t. Once again, you just have to rewrite this whole thing so that the t is by itself in the exponent. So what is that expression in parentheses? It's 1 plus 0.057 over 12. Okay, and then if you raise that to the 12th power, all right, so that's going to be the expression inside parentheses when the t is by itself. So there we have it. So since if you're multiplying by this number every year, that means you're increasing by 5.85%. Okay, so it's a little bit higher than the previous one. And then finally, continuously, the moment you see continuously, you know you need to use a different formula, the continuous compound interest formula. And that's A is equal to P e to the RT. So P is the same, E is that funny constant, R is 0.057, and T is still just T. We have to rewrite this expression just as before so that the T is by itself inside of an exponent. It's the same trick. You can write this as 200 times E to the 0.057 to the power of T. Right? That's how we can rewrite this expression. So what is that expression in brackets? Let me ask my calculator. E to the 0.057 is 1.0586. So this is 200 times 1.0586 to the t. So you can see that every year we're multiplying by this number right here, which means that every year we are increasing by 5.86% approximately, right? Notice that the 200 just didn't come into play in any of these problems. The initial amount doesn't matter. The effective annual yield doesn't care about how much you start with. The percentage increase from year to year is always the same. All right, now Number 5, an investment is made into an account. Suppose the value of the account triples after 25 years. How long will the account take to quadruple? I'm going to use an exponential model. It's kind of tricky. You might be tempted to try to use the compound interest formula since this is about money, but the information that's given is really better utilized just using the general exponential model. Y is equal to a b to the t. We don't know the initial amount, a, doesn't matter. What we do know is that after 25 years, the value of the account triples. So that means that when t is 25, the current amount, or the new amount, will be 3 times the original amount. So 25 years later, y, which is the current amount, will be 3 times the original amount, which is a, right? Equals ab to the 25. Do you see what I've done here? I've said that when t is 25, the current amount y should be 3 times the original amount a. Okay, well, you can divide both sides by a, and you just have 3 is equal to b to the 25th. B is the only unknown, so you can actually solve this equation for b. Just raise both sides to the 1 over 25th power. 3 raised to the 1 over 25 will give you 1.044 something something. So 1.0449 is equal to b. Cool. And now we want to know how long will the account take to quadruple, which means get multiplied by 4. So I'll go back to my exponential model. I now know what b is, and I'm interested in the time t when y, the new amount, is 4 times the original amount. So I will replace y with 4a, like 4 times the original amount, equals a times, and I know that b is 1.0449 to the t, and I'm interested in the value of t, which is a solution to this equation. The a can be divided by, it can just be divided off, so I have this. This is an exponential equation. We can solve it by taking logarithms. Natural log of 4 is equal to, I'll skip the usual steps, so we just get, the t comes down, right? Divide both sides by this natural log. So your answer will be t is equal to ln4 over ln of 1.0449, which should give you, let's see, natural log of 4 over natural log of 1.0449 is 31.563. Just a really quick check. Does this answer make sense? I mean, if it takes 25 years for the account to triple, we would expect it to take a bit longer than 25 years to quadruple. And so 31 is a reasonable answer, right? If you got the answer 500 billion, that would probably be wrong. Okay, so number 6, an investment of $200 is put into an account where interest is compounded continuously. That means I'm going to have to use the formula a is equal to p e to the rt. It takes 15 years for the investment to double. Okay. What is the annual interest rate of the account? That's interesting. So I'm going to use this formula. I know that 200 is what you started with, and 15 years later you have twice that, which means 400. So the new amount is 400 is equal to 200 times e to the r, which is basically the annual interest rate. We don't know what r is. That's going to be our unknown. Times t, which, how long did it take? Oops, there are my lights. Hold on. There we go. So we know that t is, 15 years in this case, so replace t with 15. This is the expression. So this is an equation. The only unknown is r. So I have 400 is equal to 200 e to the 15r. You can divide both sides by 200 and just get 2 is equal to e to the 15r. We can solve this equation by taking logarithms. It's an exponential equation because the unknown is inside of an exponent. So I have natural log of 2 is equal to natural log of e to the 15r. This is kind of nice. You can do the usual thing where the 15r comes down, but because it's natural log of e to something, the logarithm on the right-hand side becomes something very simple. It just becomes 15r. You can see that in several different ways. You can bring the 15r down if you want, and then you'd have natural log of e, but natural log of e is just 1. Anyway, we can solve for r by dividing both sides by 15. So that's my r value. I don't know what that is. Let's see. Natural log of 2 over 15 gives me 0.046 is equal to r. So remember what r is. It's the annual percentage interest rate written as a decimal. So if that is the annual percentage interest rate written as a decimal, then the interest rate must be 4.6% approximately. What is the effective annual yield of the account? Well, I can just go back to this equation here and now just plug in everything that I know. So P is 200 still. E to the, I know that R is 0.046, right? Something to the T. And to find the effective annual yield, I just rewrite this expression so that the T is by itself. So I can rewrite this as e to the 0.046 to the power of T. And then to find the effective annual yield, I just have to evaluate that expression in the brackets. E to the 0.046. Let me actually use more decimal places than that. I'm a little... All right, so that's a fuller version of what R was. So e to the 0.046209, 1.047 approximately is what I get here. So 200 times 1.04729 to the T. So this is what you're multiplying by every year. So that's giving you the effective annual yield. If you're multiplying by this, then you're increasing by 4.729%. That's the effective annual yield. Okay. All right. One more of these problems. God, there's a lot of these. A car loses 10% of its value each year. How long does it take for the car to be worth 1/5 of its original value? All right, let's use an exponential model. Y is equal to a, b to the t. Do I know the original amount a? No. Do I know b? I do. You're losing 10% each year, which means that every year it's 90% of what it used to be. And how do you make something 90% of what it used to be? You multiply by 0.9. So b is going to be 0.9, right? Do I have to divide by t here? No, it's actually good as it is because we actually want to lose 10% every single year, right? So I don't have to modify this exponent. How long does it take for the car to be worth 1/5 of its original value? Since the question is saying how long, t is definitely going to be the unknown that we're trying to solve for. We want to know the time associated with the current value being 1/5 of the original value. Y is the current value. We want that to be 1/5 of the original value, so replace y with 1/5 a. So I now have this equation. As usual, the a's can be divided off. So I have 1/5 is equal to 0.9 to the t. That's an exponential equation that can be solved using natural logs. Natural log of 1/5 is equal to t. Natural log of 0.9. Divide both sides by natural log of 0.9. So what do we get? Natural log of 1/5 divided by natural log of 0.9. I get 15.27. Something. Okay. Is that reasonable? Yeah, I think it's a reasonable answer. Okay. All right. So now we're on to a different collection of topics. We are now looking at just simplifying these exponent expressions. This is sort of more pure algebra. In this expression here, if you notice, everything that I see, 4, 2, and 8, they're all powers of 2. So I think that what I'll do is I'll just start by rewriting everything as a power of 2. 4 is like 2 squared to the third. 2 to the third. 8 is like 2 to the third. So that's 2 to the third to the negative 2. And all of this is being raised to a negative 3. Man, this is a mess. What a crazy problem. All right, well, so let's have a look. So I guess I can clean this up a little bit here. So so this is 5th root of 2 to the 6th, right? You multiply these two exponents, power of a power. Here, I'm just going to leave that 2 to the third. And then here again, you've got power of a power, so that's going to be 2 to the negative 6. Everything raised to the negative 3. So I guess, you know, in the numerator, taking the 5th root is like raising to the 1/5. So that's going to be 2 to the 6/5, right? And the bottom, I'm going to add these two exponents. So that's 2 to the 3 minus 6 is negative 3, all raised to the negative 3. I guess I'll combine these two here next. So that's going to be, let's see, 2 to the, so it's going to be 2 to the power of this thing minus this thing. Since you're subtracting a negative, you're going to wind up adding 3. 6/5 plus 3 is like 6/5 plus 15/5, right? So that's 21/5, I think, right? I just want to double check that. 6/5 plus 3 is like 15/5, so 6 plus 15, yeah, that looks good. To the negative 3, okay, now power of a power, you're going to multiply these things, so we get 2 to the negative 63 over 5, which I guess that's as simple as it gets. Cool. All right, so next one, we've got this one here. It's a similar problem, bunch of x's. This one's actually a lot easier. Just start condensing stuff. You got a power of a power. You should multiply. That's x to the negative 20, x squared over 5x to the negative 4. These two could be smashed together. You're going to add the exponents, so that's going to be x to the negative 18 over 5x to the negative 4. Several ways of thinking about this. This thing is a negative exponent, so it's going to be down. It's going to go downstairs. This guy also has a negative exponent, so it's going to trade places. The 5 is not affected by any of these exponents, so it's going to stay where it is. Up top we have x to the positive 4. On bottom we have x to the positive 18. And now there's cancellation, and we're going to have x, or no, sorry, the leftover copies of x are going to be downstairs. So 5x to the 14th. There's nothing left on top, so you have to put a 1. Right? Okay, cool. This one here, very similar. I guess I'll start by distributing this negative 2. Exponents distribute over products. Make sure that it hits the 3 as well. It is going to hit that 3, so it's like 3 to the negative 2, a to the negative 2. B is already being squared, so when you raise this object to the negative 2, you're going to have a power of a power. So it will multiply, and you get negative 4. And then we have the a to the negative 4 and the b to the negative 4, or sorry, to the positive 4. All right, so we got some things that can be combined. Let me do that. So when you combine the two a's, you add those exponents, so you have a to the negative 6. With the b's, we're going to have, actually the b's just disappear, right? You get b to the 0, which is 1. So both of these things have negative exponents, so they both go into the denominator. You get 1 over 3 to the positive 2, a to the positive 6, which of course is just 1 over 9, a to the 6th. Okay, more of these. Oh God. All right, so I guess we should distribute this negative 2 to all of these. Why did I write these ridiculous problems? So 2 to the negative 2. This thing's already being raised to the negative 1, so you raise it to the negative 2. That's power of a power. So you multiply the exponent, so that's 2. Y to the, so you distribute to this thing here. Again, power of a power, that's y to the 10, z to the negative 2. And then working on this term here, I suppose that I should distribute the negative 2 to the top and the bottom. The top will give me x to the positive 4. On the bottom will give me y to the positive 2. Okay, so what happens next? I see that so first of all, I'm going to have some stuff in the denominator because of this 2 to the negative 2. So what do we have? Let's see. So 2 to the negative 2 is going to be 2 to the positive 2 on the bottom. The z is also going to be on the bottom because it has a negative exponent, so z to the positive 2. What else is happening? We've got x's, but they're going to be in the numerator. You're going to combine them. You're going to add the exponents. So that's x to the 6th. As far as the y's go, there's some cancellation. The leftovers are going to be up top because there were more copies of y up top to begin with. So y to the 8th up top. Have I accounted for everything? I took care of that. I took care of the two x's. I took care of the two y's, and I took care of the z. So yeah, I've accounted for everything. The only thing left to do is, 2 squared. That's 4. So x to the 6th, y to the 8th over 4z squared. Okay. This one here, a lot of people get stumped on this kind of thing, but once they see what to do, it's pretty easy. You just have to distribute. Okay, you just have to distribute the y to the 1/2. So distribute it to each of these terms. So you have y to the 1/2 plus -1/2, I guess is 0, plus 2y 3/2 plus 1/2 is going to be 4/2, which is 2, but I'll just write 4/2. And then this guy here, you can think of it like this. You can think of it as y to the 1/2 over y when you multiply. All right, so what is this? Well, y to the 0, of course, is 1 plus, 2y to the 4 over 2. That's just 2y squared. And then this one here, this is like y to the 1/2 over y to the 1. So you're going to subtract. You get minus y to the -1/2, which I guess we could write as minus 1 over y to the positive 1/2, which is the square root of y if you like, but whatever. Okay, let's see, one more of these. So we've got fifth root of, all right, some more exponent stuff. So I've got x to the 5th, y to the 3rd, all raised to the 1/5, that's what that fifth root means, over x, y to the -2/5. I guess I'll distribute this 1/5 to these two guys. So that's like x to the 5 times a 5th is 1, and then 3 times a 5th is 3/5. On the bottom I have x still y to the -2/5, nothing changing on the bottom. These two x's actually cancel, that's cool. The y will go upstairs because it has a negative exponent. So there's actually nothing left in the denominator. You can write a 1 if you want, but there's not really any reason. So we have the y to the 3/5 times y to the 2/5. That's the one that went upstairs. We're just going to add these two exponents together. We can forget about the 1 in the bottom. So it's y to the, 3/5 plus 2/5 is 5/5, which is 1, so it's just y. All right. Oh my God, this thing is so long. Okay. So let's keep cracking. So solve each equation. The answer should be exact. So this is an exponential equation because the variables are in the exponent. Should we use logarithms, or can we rewrite everything as a common power? Looks like we can rewrite everything as a common power, right? 8, 16, 32, those are all powers of 2. So third root, that means, blah to the 1/3. 8 is like 2 to the 3rd, right? So 2 to the 3rd to the power of x plus 1 is 2 to the 3rd. I'll just write it out. Okay, and then 16 is 2 to the 4th, so that's like 2 to the 4th x equals 32. 32 is 2 to the 5th, right? 2, 4, 8, 16, 32, yeah. All right, so I just have to simplify the left-hand side. That's going to become 2 to the 3x plus 3 over 2 to the 4x all to the 1/3 is equal to 2 to the 5th. I can simplify this thing in brackets. It's going to be subtraction. It's 2 to the power of this thing minus the 4x. So that's -x plus 3, all raised to the 1/3, is equal to 2 to the 5th. You could distribute the 1/3 to this, or you could raise both sides to the 3rd power. Doesn't really matter. I'll distribute this since that's how I've done it in the past, I think. So I have 2 to the negative 1/3 x plus 1/3 times 3 is 1 is equal to 2 to the 5th. Okay, now I can equate the exponents. So negative 1/3 x plus 1 has to be equal to 5, so negative 1/3 x is equal to 4, so x is equal to negative 12. Cool. Next problem, this thing here, it's another exponential equation because once again the variable is inside the exponent. However, 8 and 5, there's no way you can rewrite those as powers. Common powers of the same thing, so we have to use natural logs. So take the natural log of both sides. By the way, third root of 5, if you like, is 5 to the 1/3. Okay, so what happens? The x comes down. So you have x natural log of 8 is equal to, I guess you can pull the 1/3 down if you like. It's not really necessary, but okay. And then to get the x by itself, divide both sides by 8. So you're going to get x is equal to natural log of 5 over 3 natural log of 8, which, if you want to write that as a single logarithm using the change of base formula, you can think of this as 1/3 ln 5 over ln 8 is log base 8 of 5. So that's another way of writing the answer. I'm fine with either one. Moving on. What kind of equation is this? It's another exponential equation. Can we rewrite everything as a common power? No, so we should take natural logs. Natural log of 3 to the x is equal to natural log of 4 times 5 to the 4x minus 2. This x can be pulled down. X natural log of 3. We have the natural log of a product of two things, so we have to use that first log rule to write that as natural log of 4 plus natural log of 5 to the 4x minus 2. Okay, so then we have x natural log of 3 is equal to natural log of 4 plus this exponent will come down, 4x minus 2 natural log of 5. I guess I should distribute this natural log of 5, so I have natural log of 3 is equal to natural log of 4 plus 4 ln of 5 minus 2 ln of 5. I'm worried about having enough room for this problem. I lost an x somewhere, didn't I? Yeah, right here. 4x times natural log of 5 should be an x right there. So I need to bring the x's over to one side, so I'll subtract this term from both sides. I have x. When you take this thing and subtract this guy and pull out the common factor of x, you have natural log of 3 minus 4 ln of 5 is equal to ln of 4 minus 2 ln of 5. Okay, and then to get the x by itself, you have to divide both sides by this expression here. So doing that, I'm going to get, what a lovely problem this is. X is equal to natural log of 4 minus 2 ln of 5 over natural log of 3 minus 4 natural log of 5. That's an exact answer. I think it can be simplified. If you like, this is like, what is it? You can put the 2 on the inside there. That's like 25. And then it would be 4 over 25. Same thing here. If you put the 4, oh god, that's a huge number. 5 to the 4th. What's that? 625, maybe? Yeah. So this thing goes on the inside. It'll become 625, and then you've got log of 3 minus log of 625, so it's 3 over 625, which, I guess if you really want to write that as a single logarithm for some reason, you could write that as log base 3 over 625 of 4 over 25, which I don't know if that's any better. Any one of these. I think I like this one the most, but that one is also fine. Okay, moving on. We have this equation here. Oh, look at that. We've got variables stuck inside of logarithms. That means that it is a logarithmic equation, which means we need to start, if we can, by condensing logarithms. I've got one log plus another, so I will multiply these two guys. 5x plus 10 is equal to 4. Okay, I've condensed the log. Let's now exponentiate by the base of the logarithm. So if I exponentiate both sides by 2, Okay, what do I get? On the left-hand side, I just have 5x plus 10. Right-hand side, I have 2 to the 4th, which is 2, 4, 8, 16. All right, subtract 10, divide by 5. 6 fifths. Cool. This thing here, all right, it's another exponential equation. Can we rewrite it as common powers of the same number? Yeah, I think we can. 1/2 and 8, 2 and 8, those are both powers of 2, right? Actually, 1/2 is 2 to the negative 1, isn't it? Right? So it's like 2 to the negative 1 to the 4 minus x is equal to 2 to the 3rd. So, all right, multiplying, I have negative 1 times 4 minus x is just negative 4 plus x is equal to 2 to the 3. Okay, so now equate the exponents. I have negative 4 plus x equals 3. Add 4, I get 7. Great. Another logarithmic equation. Let's condense logs on the right-hand side before we exponentiate. So I'm going to multiply the insides of these two logarithms. That's going to give me 6x. Yeah, now I can exponentiate. I'll skip the intermediate step. If I exponentiate both sides by 2, the left-hand side I'm just going to be left with this. The right-hand side I'm just going to be left with this. Okay, it's a quadratic equation. Let me put everything on one side. Subtract 6x. Probably I should factor. Pair of numbers that multiply to 8 add up to negative 6. Negative 4 and negative 2, right? So x minus 4 times x minus 2 is equal to 0. So I get the two solutions. X is equal to 4 and 2. Cool. 20. Yeah, I give you a hint on this one. Make the substitution u is equal to 9x. Yeah, so if you make u equal to 9x, that tells you that u squared is equal to 9 to the x squared, which is 9 to the 2x. That's useful because 9 to the 2x is exactly what you have right here. So you can replace that 9 to the 2x with u squared minus 2 times 9 to the x, that's just u, minus 3 equals 0. Well, that's a quadratic equation. We can solve it. Pair of numbers that multiply to negative 3 and add up to negative 2. I guess that would be negative 3 and 1. Cool. So we find that u is equal to 3 or u is equal to negative 1. Of course, I don't care about u, I care about x, so I should go back to x. What was u? U was 9 to the x. So 9 to the x is equal to 3, or 9 to the x is equal to negative 1. Basically these are both exponential equations. This one here is sort of, 9 and 3 are both powers of 3. You can say that's 3 squared to the x is equal to 3. That's going to tell you that 2x is equal to 1, so x is equal to 1/2, which maybe you could have just guessed by looking at this equation here. This equation has no solutions, basically because exponentials are never negative. Like 9 to the x cannot be a negative number. It doesn't matter what you raise 9 to, you will never get a negative number. All right, so x equals 1/2 is the only solution. All right, let's see. If I remember, this problem is kind of a nightmare, at least in terms of simplification. Yeah, so it's a logarithmic equation. There's nothing to condense. We should just exponentiate by the base of the logarithm, which is e. So if I exponentiate the left-hand side by e, I just get x to the negative 1 plus 2 is equal to e to the negative 3. Okay. X to the negative 1 is like 1 over x. Okay. As far as how to, solve this, basically, several ways of doing it, but basically, let me put it to you this way. If I subtract 2 from both sides, I have this. One way of solving this is to regard this as a fraction and then cross multiply, or alternatively, you could invert both sides of the equation. Like if you have one fraction equals another fraction, you are allowed to just flip them both upside down and invert both sides of the equation. That's what I'll do. So invert this side, you just get x. Invert this side, you just get 1 over e to the negative 3 minus 2. There are lots of different ways of writing that answer, but I don't really care. All right, so this guy here, what's going on with this thing? It's an exponential equation. I think we need to use logarithms. Yeah, so I'll take take the natural log both sides. 5e to the 3x minus 1 is equal to the natural log of e. Here you have a product, 5 times e to the blah, blah, blah. So you need to rewrite that as ln of 5 plus ln of e to the 3x minus 1 equals ln of e. A lot of this stuff is going to clean up. Natural log of 5 just is what it is, but natural log of e to the 3x minus 1 is just 3x minus 1. Natural log of e is just 1. All right, so now just get the x by itself. I guess add 1 to both sides and also subtract the natural log of 5 from both sides. So I have 3x is equal to 2. That's from adding the 1 to both sides. And then minus the natural log of 5. And now just divide both sides by 3. So I have x is equal to 2 minus natural log of 5 over 3. Cool. That's my answer. Jeez. Another one of these. Okay. So let's see. Make the substitution u is equal to 3 to the x. Then u squared is equal to 3 to the 2x. If you multiply both sides by 3 here, you get 3u squared is equal to 3 times 3 to the 2x, which is equal to 3 to the 2x plus 1. In other words, this expression here is just 3 to the 2x plus 1. Or if you like, it's this. I think it's better to replace it with that. Yeah, so it's 3u squared. That's what I'm getting at. This expression here is 3u squared. So that's 3u squared minus 7. 3 to the x is just u plus 2 is equal to 0. Solve this quadratic. Oh, jeez. Does this have to be factored using like grouping or something? Yeah, you know, I'm just going to write etc. Okay? I mean, it's not algebra 2. I don't have time for that. It's kind of funny how I write these problems and then I start doing them and I'm like, I don't want to do these problems. All right. Graphing logs, you know, I mean, I don't really care that much about graphing logarithms, to be totally honest. You know, I mean, this is just, it's not that important of a topic. I just want you to see what some log graphs look like, basically. I mean, you know, I tell you to graph these functions by using a table of x, y values, I'll just give you one example of how this goes. This is not something I'm really going to test you on, but you know, you should sort of know what I'm talking about. Let's just do the second one, 25. Okay, so here's a table of x, y values. Just pick some x values, evaluate the function, and then that'll give you a bunch of points, and then you connect the dots. That's graphing by point plotting. Problem is, you need to pick good x values for which you can actually evaluate the function. Like if I pick x equals 5, I plug it in, I get log base 3 of 5. Well, I don't know what that is. So I'm going to pick values of x that I know I can actually evaluate this for, like 1. What is log base 3 of 1? That's 0. How about 3? What is log base 3 of 3? That's 1. How about 9? What is log base 3 of 9? That's 2. Okay, and yeah, that's probably good enough. So I got these 3 points, 1, 0, 3, 1, so that's right here, and then 9, 2, let's say 3, 6, 9, 2, like this. So you can see that the graph kind of looks something like this. You might wonder what's happening here. If you investigate with your calculator, you can see that there's actually a vertical asymptote, and it actually kind of goes like that. Interesting behavior, but not anything I really care too much about. Okay, moving on to the last page here. All right, so suppose that ln of x is equal to 2 and ln of y is equal to 3. Evaluate each expression. So the idea here is to split this up into basically in terms of ln x and ln y. So this is going to give me ln of e to the third minus ln of x squared y, right? That's using the second rule of logs. Natural log of e to the third is just 3 minus, and then here, you know, I can rewrite this as a product. This is natural log of x squared plus natural log of y. Notice that I put this in brackets. The reason why is you're supposed to subtract this expression. Well, natural log of x squared y is this entire thing. So you should be subtracting this entire thing. Anyway, that's 3 minus natural log of, the 2 can come out here, right? That's what I'm getting at here. And then plus natural log of y. And the point is I actually know what natural log of x and natural log of y are. I tell you, they're 2 and 3 respectively. So yeah, so I get 3 minus 2 times natural log of x, which is 2, plus natural log of y, which is 3. And so that's whatever it is. 4 plus 3 is 7. So this gives me -4. Okay. These next two examples are very similar. So seeing that square root, I know that that means ex squared y to the third to the 1/2, and that the 1/2 can be pulled out on the side. So we have this. Cool. And then we've got the product of a bunch of things. So I'm going to write that as a sum. 1/2 quantity ln of e plus ln of x squared plus ln of y to the third, right? And then finally, I guess, well, natural log of e is just 1. This thing is 2 ln of x, and then this thing is 3 ln of y. And then we just have to replace these values. Natural log of x was 2. So that's 2 times 2 plus 3. Natural log of y I said was 3. So this is, let's see, 1 plus 4 is 5. Plus 9 is 14. Divided by 2 is 7. Okay. One more of these. We're almost done. Thank God. Let's see. So I guess I'll start by writing this is natural log of e to the 5th minus natural log of the denominator. That third root is telling me that it should be like all that stuff raised to the 1/3, right? Natural log of e to the 5th is just 5, but here the 1/3 can be pulled out, so that's 1/3 natural log of xy squared. So that's 5 minus 1/3 quantity ln of x plus ln of y squared. You know, the 2 can come down, so we have 5 minus 1/3 quantity natural log of x plus 2 natural log of y, and we now can replace each of these things. So this is so natural log of x is 2 plus 2 times natural log of y we said was 3. So that's, I don't know, whatever it is, who cares? It's just some arithmetic at this point. All right, so one more, or a couple more. So this one here, this sort of just reminds you that you have to know what logs actually mean. This is the power of 2 that gives you 32. I don't know what that is. 2, 4, 8, 16, 32. I guess that's 5. Is 5 somewhere on the right-hand side? Yeah, it is. Okay, so I guess that's that one. 4 times log base 3 of 2. Let's see. That's 4 times, well, I don't really know what it is exactly, but you can put the 4 on the inside and get log base 3 of 2 to the 4, which is in fact log base 3 of 16, isn't it? So that's that one. Log base 7 of 8. By the change of base formula. That's that thing right there. Right, that's the change of base formula. Log base 7 of 1 over 49. That's definitely just -2. Log base 36 of 6, that's a half. Okay, so that's the end of that. This thing here, you just need to use the change of base formula. It's natural log of 7 over natural log of 3, and then you can use your calculator, and you'll get that answer right there. This guy here, rewrite this thing as a single logarithm. You know, the numerator is going to be natural log of 15 over 5, which is natural log of 3. This one here, you can put the 3 on the inside of the natural log of 2. That'll be natural log of 2 to the 3rd, which is 8. So, and then it'll be like natural log of 8 minus natural log of 4. So I have natural log of 3 over natural log of 2 because it's, you know, subtracting 2 logs. You divide the 2 insides. And then this can be rewritten as a single logarithm, log base 2 of 3. Okay, that's it. Well, you know, I know that was quite a lot of review. Hopefully this is helpful. All right.